In this presentation, the basic concepts of internal fixation with screws and plates are shown and practiced. The objective is to understand the principle of interfragmentary compression that provides absolute stability. There are two main parts: screw technique and conventional plating. The screw technique. First, a 4.5 millimeter Cortex screw will be applied without a gliding hole to function as a position screw. By over-drilling the near cortex, interfragmentary compression can be obtained. A 6.5 millimeter cancellous bone screw is used to demonstrate interfragmentary compression of a medial tibial head fracture with a lag screw. Conventional plating with the LCP, or locking compression plate. The 4.5/5.0 LCP is used as a standard compression plate and as a compression plate with a lag screw through the plate. Then there's the LCP-L plate, which is a buttress plate. The screw technique. The standard 4.5 millimeter Cortex screw below and the 6.5 millimeter cancellous bone screw above are used in these exercises. The 4.5 millimeter Cortex screw has a thread diameter of 4.5 millimeters and a core diameter of 3 millimeters. The 6.5 millimeter cancellous bone screw has a thread of 6.5 millimeters and a core diameter of 3.2 millimeters. It's available with a 16 millimeter thread, a 32 millimeter thread, or fully threaded. The following instruments are required: the 3.2 millimeter drill bit, which is slightly larger than the core diameter of the screw, and the 4.5 millimeter drill bit, which is the same diameter as the thread of the screw. The 4.5/3.2 double drill guide. The countersink. The depth gauge. The 4.5 millimeter tap for Cortex screws and the T-handle. And the large hexagonal screwdriver. The generic bone is fixed in the bone clamp. Using the 3.2 millimeter drill bit and the 3.2 drill sleeve, both cortices are drilled through, perpendicular to the fracture plane. The depth gauge is used to determine the required screw length. The thread is cut using the 4.5 millimeter tap and the corresponding sleeve. The 4.5 millimeter Cortex screw is inserted. Compression between the screw head and the bone surface is obtained, but as both the near and far cortex are threaded, the fracture gap will not be closed or compressed. This screw is called a position screw. The mechanism is now illustrated. The gap will not close because the thread of the screw is engaged in both cortices. To achieve interfragmentary compression, the hole in the near cortex must allow axial gliding of the screw. This is obtained by over-drilling the near cortex with the 4.5 millimeter drill bit. This is called the lag screw technique. At the other end of the bone model, first a gliding hole through the near cortex perpendicular to the fracture plane is drilled using the 4.5 millimeter drill bit. The 3.2 drill guide is inserted into this hole to direct the 3.2 millimeter drill bit used to drill the far cortex. This ensures that the 4.5 millimeter gliding hole and the 3.2 millimeter thread hole are aligned. Countersinking the hole in the near cortex reduces screw head prominence, which is advantageous in areas of minimal soft tissue coverage. The depth gauge is used to determine the required screw length. A thread is cut in the far cortex using the 4.5 millimeter tap through the drill sleeve. A 4.5 millimeter Cortex screw is inserted. As soon as the screw head touches the bone, further tightening of the screw will lead to closure of the fracture gap and interfragmentary compression. The screw is removed and the bone model rotated. A lag screw is inserted as before. The only exception is the orientation of the lag screw relative to the fracture plane. When the lag screw is not placed perpendicular to the fracture plane, shear forces develop. They can cause displacement of the fracture fragments, as shown in this demonstration. The cancellous bone screw. The 6.5 millimeter cancellous bone screw is used to demonstrate interfragmentary compression of a medial tibial head fracture with a lag screw. The following instruments are required. A 1.6 millimeter K wire with the 2.0 triple drill guide, the 3.2 millimeter drill bit. It has the same diameter as the core of the screw, and the 6.5 3.2 double drill guide. The depth gauge. The 6.5 millimeter cancellous bone tap, which has the same diameter as the thread of the screw, along with the T-handle. A 6.5 millimeter cancellous bone screw with a 16 millimeter long thread and a washer, and the large hexagonal screwdriver. The fragment is reduced and fixed with the pointed reduction forceps. For preliminary fixation, a K-wire is inserted parallel to the joint, avoiding the previously planned position of the screw. The hole is drilled with the 3.2 millimeter drill bit and drill sleeve without penetrating the opposite cortex. The depth is measured. The near cortex is tapped with the 6.5 millimeter tap and sleeve. In young patients with good bone quality, the entire length of the hole should be tapped. A 6.5 millimeter cancellous bone screw with a short thread and a washer is inserted. In its final position, the entire threaded portion of the screw must lie beyond the fracture plane to achieve interfragmentary compression. The required compression is achieved by tightening the screw. With dense bone, a washer may not be required. The K-wire and the reduction forceps are removed. Depending on the fracture pattern, a second screw or a buttress plate may be needed. Conventional plating technique. The first part of this exercise will show the LCP used as a standard dynamic compression plate. The unthreaded half of the combination hole, known as the dynamic compression unit, accommodates standard 4.5 millimeter screws used for axial compression. Wide angulation of the screws is possible. The Cortex screws can be used to achieve dynamic compression of the fracture when inserted eccentrically. They also can be placed neutrally, just to fix the plate onto the bone. The threadless part of the combination hole always faces towards the end of the plate. The space between the two inner combination holes where the threaded portions face each other represents the center of the plate. Based on this symmetry, dynamic compression can be achieved from both sides of the plate. To start the exercise, one end of the generic bone is fixed in the clamp. The 8-hole LCP is positioned on the intact bone, marking the site where the transverse osteotomy is to be done with the oscillating saw. The plate is placed and secured with bone-holding forceps to the bone fixed in the clamp so that the center of the plate lies over the osteotomy. The plate is now fixed in place with one screw. The 4.5 3.2 universal drill guide is used to direct the drill bit and protect the soft tissues. To obtain dynamic compression of the fracture, the drill sleeve must be placed eccentrically against the smooth border of the combination hole away from the fracture. To do so, the spring-loaded drill sleeve may not be pressed into the plate hole. The insert therefore remains flush with the outer sleeve. Alternatively, by pressing the drill guide down against the bone, it will be centered in the compression unit of the combination hole. In this neutral position, no additional movement or compression will result from screw insertion. The spring-loaded insert now protrudes from the outer sleeve. With the drill guide in the neutral position, a 3.2 millimeter hole is drilled through both cortices. The depth gauge is used to determine the required length. The thread is cut in both cortices with the 4.5 millimeter tap. The soft tissues and the plate surface are protected with the appropriate protection sleeve. A 4.5 millimeter Cortex screw is inserted and tightened. The second half of the bone is reduced and fixed to the plate with the bone-holding forceps. Without applying any pressure to the universal drill guide, a 3.2 millimeter eccentric hole is drilled. The length is measured. When driving home the screw, the head hits the smooth slope of the plate hole. The bone is moved axially, creating compression of the osteotomy. However, this compression occurs only beneath the plate in the near cortex, while a slight opening of the osteotomy in the far cortex can be observed. Here the point is illustrated. The widening of the gap in the far cortex can be avoided by overbending the plate like this. To begin, the screws and the plate are removed. The plate then is slightly overbent with the bending press. The same osteotomy is now fixed with the overbent plate and the screws. For optimal compression without loss of reduction, it's recommended to sequentially tighten the screws. The gap is now closed, and the bone is compressed over its entire cross-section. A stable and anatomically correct internal fixation has been achieved. In this exercise, the function of a compression plate in combination with a lag screw will be shown. A new bone with a simple oblique type A2 fracture and a black foam sheath to simulate the periosteum will be employed. The same 8-hole LCP is used. The plate is fixed on the bone with the bone-holding forceps. The position of the plate is defined by the planned direction of the lag screw. Compression of the fracture will be obtained in the axial direction by 2 eccentric screws and 1 interfragmentary lag screw. To prevent gliding along the oblique fracture plane, the fragment forming an open angle to the plate must first be fixed in place. The sharp edge of the second fragment will then be wedged in. Optimal axial compression of the fracture can be achieved. A hole is drilled in the neutral position with the 3.2 millimeter drill bit and the universal drill guide. The length is measured. After tapping, the screw is inserted and tightened. The reduction is verified. To compress the fracture, the plate will be fixed to the other bone segment with an eccentrically placed screw. Using the universal drill guide and the 3.2 millimeter drill bit, a hole is drilled in the eccentric position. The length is measured and the hole tapped. The screw is inserted and tightened. Axial compression of the fracture is obtained. Again, a slight gap in the far cortex is seen. It widens when bending the whole construct. To improve the stability by compressing the oblique fracture, a lag screw will be inserted perpendicular to the fracture plane. The near cortex is drilled with the 4.5 millimeter drill bit and the corresponding drill guide to create a glide hole. The 3.2 millimeter drill guide is inserted into the previously drilled hole, and a 3.2 millimeter thread hole is drilled through the far cortex. The screw length is determined with the depth gauge. The thread in the far cortex is cut with the 4.5 millimeter tap. The selected 4.5 millimeter cortex screw is inserted. Tightening the screw produces additional interfragmentary compression of the oblique fracture plane. Absolutely rigid fixation of the fracture has been achieved by pre-loading the construct as well as producing friction at the fracture site. The fixation is finished off with two more 4.5 millimeter screws at either end of the plate. However, the periosteum has been compressed as well, which interferes with the cortical blood supply. In this exercise, an LCP-L plate as a buttress plate with lag screws is demonstrated. Intra-articular fractures are usually produced by shearing and bending forces. Fixation by lag screws only often cannot prevent secondary displacement in poor quality bone. Such displacement can be overcome by applying a plate to serve as a buttress. A split wedge fracture of the lateral tibial plateau is reduced anatomically and held in place with the large pointed reduction forceps. The plate may be used as a guide when securing the provisional fixation with two 1.6 millimeter K wires inserted at 90 degrees to the fracture plane so as not to counteract subsequent compression. The forceps is removed. A pre-contoured L plate is used as a buttress plate in this type B1 tibial plateau fracture. However, it may need additional contouring to the bone, otherwise it could either fail to buttress or it could cause a deformity when secured to the bone. Once the plate fits the contour of the bone exactly, it's securely fixed to the bone. It's best to start the fixation of the plate on the diaphysial side using the elongated hole, which allows some fine-tuning of the plate position. The plate is fixed to the bone with the screw in the neutral position in the usual manner. To secure the split wedge fragment, a 6.5 millimeter cancellous bone screw can be inserted either through the plate or independent of it. It's important that the lag screw be placed where it will provide the best compression of the articular fragments. In this case, the cancellous screw is inserted through the plate. After drilling with the 3.2 millimeter drill bit and measurement of the depth, the near cortex is tapped. Here, a cancellous screw with a 32 millimeter long thread is inserted. For a screw to act as a lag screw, the thread must not cross the fracture line. The second cancellous screw is inserted. The screws are tightened alternately. The K-wires are removed. The most distal plate hole is filled with a 4.5 millimeter Cortex screw. The fit of the buttress plate is snug. Compression has made the fracture line almost invisible.